and you can ask your question directly to the teacher, or you can send your question by chat, okay? Okay, Elias, 1 hour of class, okay? Okay, guys, enjoy the class.
Please allow me to share the screen.
Are you all ready?
Okay. So in our last class, we discussed about the different theories that how we can place electron in the shells and in different subshells, and how cylinder wave equation help us to find the position of electron. So now today we will discuss the topic of electron energy levels, and we will study how we can place different number of electrons in the shells and subshells. So this is also called as atomic states, and we will discuss how many number of lines or how many number of spectrum will be generate if electron jump from the higher shell to lower shell, and if it jump from lower shell to higher shell. So here is energy levels and transition. We know that an atom has different number of shells around them, and the space around the nucleus where the electrons revolve within a specific principal quantum number are called as energy levels, and the same space is called as principal quantum number. So an atom may have different quantum numbers, or this is also called as principal quantum numbers, and it is represented by the small n. And look at the diagram. This is at the central dark in the purple color is called as nucleus, while this is the first shell, and it is called as first energy level that contain 2 electron, and this is the second energy level, and so on. There are many energy levels that goes on increasing according to the number of electron in the shell. What are the orbits and nodes? The space or region where there are 95% of chances of finding an electron, or we can say that the probability to find the electron, if it is 95%, then we can say that it is an orbit, or also this is its second name is shell. So look at the dotted circles. These are the orbits, or we can say that these are the shell, while the space between these n1 and 2, this is the simple space that is in white color, is called as node, and there are just 0% chances of finding an electron, and we can say that there are no chances of electron residing in the space of node. How principal quantum number help us in finding the electron? Basically, the principal quantum number tell us about the distance of electron from nucleus, and it also tell us about the number of shell, and about the energy of electrons, and also about the size of orbit. So in the previous slide, look at the number of shells. So this is this n1 and n2 and 3. These are principal quantum number, and this will tell us about the distance. So this blue arrow can specify the distance from n1 shell to n3 and so on into infinity. So also this is also tell us about the size of shell. The first shell that is in low space, while the second shell is in large space, and so on. The cell size increases as it number of electron increases. So I'll tell us about the size of orbits and also about the energy. It means that the electron that are revolving in the nearest to the nucleus that have low energy, while that electrons that are revolving in the principal quantum number of shell 2 that have higher energy than the n1, and so on. N3 will have higher energy than the n2, and n4 will have higher energy than the n3. And how we can find the total number of electron in shell? So all of you please consider it at the terms that we will use in the questions. So how we can calculate the number of electron in shell, or also it is called it as orbit. So the formula to calculate the number of electron in shell or orbit is called as 2 equal to n n square. We can calculate number of electron in the any shell. So there are some calculations about the first shell 2 and 4, and we will see how they help us in the counting the number of electron. So representation of shell in the principal quantum number is represented by the n1, n2, n3, and n4. N1 shell is called as K shell, and n2 shell is called as L shell, and n3 M, and so on. This counting goes on. The n1 shell, which is contain 2 electron, and we can calculate the number of electron in one shell by formula 2n square, and n is the principal quantum number, and it start always from the 1. Its value cannot be 0. So 2 into 1, and 1 square is equal to 1. So 2 multiplied by 1 is equal to 2. This means n1 shell or K shell will have only 2 electron. Similarly, n2 shell, which is also called as L shell, which have 8 electron and can be justified by the formula 2n square. 2 bracket 2 square 2.
Elias, Elias, are you there? Teacher. Oh, Alex, we want to wait a couple of minutes. The teacher have some difficulty with the connection. Okay, just wait 1 minute. Okay.
Okay.
Okay. So the shapes of orbitals are represented by the azimuthal. So the shapes of orbitals are represented by the azimuthal quantum.
Hey guys, we want to wait a couple of minutes. The teacher have some trouble with the connection. Just wait, okay? Because he tried to connect now.
Sorry. So these azimuthal quantum number values can be represented by the formula L equal to n minus 1. And this formula can be used to calculate the different subshell in the shell. While formula to calculate the number of electrons in the subshell is 2 into 2L plus 1, and this can also be written as 4L plus 2. And a formula to calculate the number of subshell in the shell is equal to n. This means if we can count, and if we want to count the number of subshell in any shell, then we can use just this formula to calculate the number of subshell in any shell. It means that first shell will have one subshell, and the second subshell will have 2, and similarly goes on, while n is a quantum number, principal quantum number, and this will show that third cell will contain 3 subshell S, P, D, and 4 shell will contain 4 subshell. Number of electrons in the subshell. For S subshell or with the L value 0, the L value always start from the 0, and we in the last slide we said that the value of L always be less than n. Here the value of L always be n minus 1. This means L and n can never be equal to each other. So for S subshell starting with the value L0, then we can put the value of L0 to the formula to calculate the number of electrons. So 2 into 2L, and put the value of L into the L. So 2 into 2 into 0 plus 1. So 2 into 0 is 0, and the answer will be equal to 2. This means S subshell will have 2 electrons, and similarly for counting the number of electrons in the P subshell, we can put the L value 1. So for S, we can put the value of L equal to 0. For P, we can put the value L equal to 1. And for D, we can put the L value to 2. And for F, we can put L value equal to 3. And we can calculate the number of electrons in the subshell by this formula. So we can say that S subshell will have 2 electrons, and P subshell will have 6 electrons, D subshell will have 10 electrons, and F subshell will have 14 electrons. And these electrons are counted by the this formula 2 into 2L plus 1. So here are some questions. How many subshell will be present in the K, L, and M shell? So we can start this by So our question is that how many shell are present in the K, L, and M shell? So K is a N1, while L is N2, and M is N3. And recently we studied the formula to calculate the number of subshell in any shell is equal to N. This means the number of subshell will be equal to the number of principal quantum number. If we have N1, this means in shell 1 we have just one shell, that will be equal to S subshell, and for N2 we have 2 subshell, that is equal to 2, and we will have S and P subshell. This is K and this is L, and for M that will be equal to N3, and this N3 is represented to that this is our nucleus. This is the first shell, this is the second shell, and this is the third shell. This first shell is K shell, this is L shell, and this is M shell, and this is represented by number 3. And for this we will have number of subshell will be S, P, and D. So we can say that in K shell we have just one subshell, in L shell we will have 2 subshell, and in M shell we will have 3 subshell. So represent the electronic configuration of carbon and sodium atom in term of subshell. In term of subshell mean by S and P. So we can represent it this by. So carbon has 6 electrons, and we can write this configuration as 1s that contain 2 electrons, 2s that contain also 2 electron, and last shell that called as 2p, and that will contain only 4 electrons. So these are the subshell that contain number of electrons in them. And similarly for sodium ion, that is Na, and we can represent this 1s, and this sodium contains just 11 number of electron. So this is 1s that contain 2 electrons, and this is 2s 2 and 2p, and this is 3s that contain just 1 electron. So these are the total 11 electrons, 6, 2, 2, 10, and 1. These are the total 11 electrons in the different number of subshell. Okay. Next are the magnetic quantum numbers, and magnetic quantum numbers are basically magnetic effect of electrons. And we know that electrons always revolve around the nucleus, so their movement produce a magnetic effect around the nucleus, and that is called as magnetic quantum number. And the magnetic quantum number is the origin of atomic orbitals. So it is related to the as a mutual quantum number, and we represent magnetic quantum number by a simple n. And these value plus to minus are representing dash. This plus L means that showing a positive spin, while this negative sign representing that the negative spin of the electrons. So its value may vary from plus to minus by any number. So formula to calculate the magnetic quantum number is equal to 2L plus 1. Just in the previous as a mutual quantum number, we have formula 2L plus 1, and for magnetic quantum number we have just remove the 2. So for magnetic quantum number, how we can calculate the atomic orbitals for S subshell, and similarly how can we calculate the atomic orbital for P subshell, and so on for F and D subshell. So for S subshell, we know that simply S represented by L equal to 0. So this formula put the value of L into this formula, and L is equal to 0 for S subshell. So M equal to 2 into 0 plus 1, and answer will be 1. This means that S subshell will have just one orientation in the space, and magnetic number quantum numbers are the numbers that help us to represent the number of electron in the different orientations in the 3D space. So this formula is saying that for S, hello. Oh, okay. So for S subshell, we can say that S subshell have only one orientation, and we can put S subshell into any place, and we do not have to specify the orientation of S subshell for positive and negative rotation. While for the P subshell, we have just 3 value of magnetic quantum number, and that will be by the formula 2L plus 1. And for P subshell, we can put the value of L equal to 1. So by putting 1, answer will be 3. This 3 means we have 3 value of magnetic quantum number, and that can be represented by the plus 1, 0, and minus 1. And these will be the 3 value of P subshell: positive 1, 0, and negative 1. These will be the 3 magnetic quantum number of P subshell. Similarly, for the D subshell, we can put the value of L equal to 2, and then the answer will be equal to 5. For that mean, we will have 5 orientation or 5 magnetic quantum number for the D subshell. And similarly, for the F subshell, we can put the value of L equal to 3, and the answer will be equal to 7. So for F subshell, there will be 7 orientations in the space in which we can put the number of electrons different way. So these are basically ranges of electron by positive to negative integers. So here are question: calculate the number of orbitals in third shell of atom. Now we have to calculate orbitals in the shell, and for that we have formula n square. We can count the number of orbitals in for any shell by the formula n square. for to count the number of orbitals are equal to n square. This means if we are counting for the first shell that have this is the principal quantum number, and we know that these are represented by the n. So for the first shell, the quantum number will be 1, and by scaling that, we can say that the answer will be 1. This means that there are just 1 orbitals for the s subshell, and the s subshell only contain 2 electrons. So for the second shell that is represented by 2, we can put the formula n equal to square. This is the second shell, and 2 equal to square, and the answer will be equal to 4. This means that the second shell will have 4 orbitals number that will be equal to s, p, and there are 3 orientations for the p cell. So this will be represented in the different orientations of px, py, and the last one is pz. So that's are 4 orbitals for the second shell, px, py, and pz, and the one only s that do not have any orientations, and we can put it in anywhere. So for the third shell, we can just put that number 3, and we can scale that the answer will be 9, and we can say that third shell will have 9 orientation or 9 orbitals that will be equal to by the 1s, 3p, and 4 d subshell. So that will be 1s, 4p, that are px, py, p, and z, and 5 orientations of d subshell. So there are 5 orientations for the d shell, and we can count that 5, 3, and 1. So that's totally comes 9. Okay, how many electrons can reside in one orbitals? So the answer is simple. In one orbitals, there are only 2 electrons can we put them, or we can say that in one orbitals, only 2 electrons can reside in it. So the next is spin quantum number, and the spin quantum number tell us about the spinning orientations of the electrons, and that can be in the form of anti-clockwise rotation, or that may be in the form of clockwise rotation. The anti-clockwise rotation is represented by the positive sign, while the clockwise orientation are represented in the negative sign. So there are chances of and equal chances of orientations or maybe spin, and this is also called as self-rotation of electrons. There are nothing, any force that uh, make electron to rotate in any direction. They are independently rotating in their directions, and that's why they are also called as self-rotation. So that can be anti-clockwise, and that can be positive or anti-clockwise, or that can be clockwise direction. So there are equal chance, we can say that there are 50-50 chances for the anti-clockwise rotation and 50% chances for the clockwise orientations. So here are the question: which one of the following represent correct placement of electrons in the potassium-19 last shell. This means that potassium will have 19 electrons, and in the last shell, so this is a potassium that contain 19 electrons, and we can just say that that is a nucleus. That is the first shell that contain 2 electrons. This is the second shell that contain 8 electrons, and that is the third shell that will contain 8 electrons also, and that become total 18, and the fourth shell that left only 1. This means our potassium has 19 electrons, and 2, 8 and 8 become 18, and 1 plus 19. This means the last shell of potassium has only 1 electron. And how we can represent the uh, uh, orbitals orientations of the potassium last electrons. So we can say that this last electron is present in the fourth subshell. So here is n will be equal to 4. So, and we can say that the L value equal to 0. Why this is 0? Because we know that this is the S subshell, and we can represent the electronic configuration of potassium by a simple electronic configuration of potassium is 1s, 2s, sorry, 2p, and that will be 3s. That contain 2 electrons. This will also 2, that is 6, and that will contain 2, and this becomes 6, 2, 2, 10, 10 and 2, 12. Similarly, that will count that and end up with the fourth S shell. So this is showing that the last electron that is present in the S subshell of potassium. So for S, we represent by L by the 0 value, and so M value will be equal to 1, and or it may be 0, and we know that there are just one orientations of the S subshell, and the rotation of electron can be plus 1 by 2, or it may be minus 1 by 2, because we say that there are 50% chances of anti-clockwise rotation or clockwise rotation. So there are possibility that both of these will be present, but we represent just this by one orientation because we have just one electron in the shell. So we can represent by positive or by negative. We can just use just one because we will have only just one electron at the last shell. So here in the slide, the correct answer will be equal to n will be 4 and L will be 0, while M that showing the orientations will be equal to 1 and S will be positive 1 or it can be negative half. And remember that the value of L or M can never be equal or can never be greater than L. The value of M cannot be greater than L, and value of L cannot be greater than N. So we can say that N equal to 4, that's showing our electron in the 4 shell, having electron in the S subshell. L is equal to 0, and just have one orientation, that is represented by the M equal to 1. And this orientation or spin can be represented by the positive or negative orientation. So the option will be correct. So here are more, and which one of the following represent the correct placement of electron in the neon law shell? And we know that neons are the noble gases that have complete law subshell. So neon have 10 electrons, and the first shell contain just 2 electron, and the second shell contain 8 electron. So for this, we can say that the n value can be 2, because we are considering the last shell of the neon. So neon just have 2 cells. So that will be n equal to 2, and the value of uh, placement of electron can be 0 and 1. Why? Because we know that there are total 8 electron in the last shell, and that will be gained by the S or by the P subshell. So this positive one is represented that can be Px, Py, and Pz. These are the ranges of as a mutual quantum number for this electron, and this is the range of 0 for S subshell. And the value of M, that is here showing that there are 3 orientations for the L shell. So, and the number of spinning electrons can be represented by the positive and negative. And why we are using both of these? Because we know that electrons, the neon has complete subshell. So that why we are using both positive and negative orientations for the neon shell. So the first option is not correct, because both of the orientations are in the same direction, and this is not okay for the any atom to have same rotations of the electrons in the shell. So which one of the following is not correct? So this B option is correct for the neon. And which one of the following is not possible? And we can eliminate both of the options by just considering the value of N and L and M. And we know that N always greater than L, and L can be equal to the M or maybe greater than the M. So which one of the following is correct? So here are the options. We can say that L equal to 1. This means that there will be P subshell that will have 3 orientations, while there are this showing that M will have just 1 orientations for the S shell. So this is wrong. And similarly for this is showing that N in the 4 shell, and that is equal to L is equal to 0, mean that is the electron that is present in the last shell is S, and just have 0 orientation. That is incorrect, because the S subshell has just 1 orientation. And here are the option N equal to 2, L equal to 0, and M equal to 0. And similarly for these are both the same option, just we have reversed the direction of electron, but the both options are wrong. And similarly in the D option, N is equal to 3. This means L is equal to 2, and L is 2, showing that we have how many orientations of the electron, that will be equal to 5. There will be 5 orientations for the electron, while we have just in the option 3. So that is the wrong option, and that is the correct option in the A option. Which one of the following is not possible? And this is a similar question as present in the last, and you can use the n or shape of orbitals to find the correct answer. So number of electron in the orbitals for which n is equal to 3 and L equal to 1. This means that we are considering N3 and our L equal to 1. And this L1 equal to means that is representing the P subshell. So this this N is representing that we have third shell of electrons, and this P is represented that we have P orbital of third shell. So how many electrons can be present in the 3p subshell? And that will be maybe option that we can use 6, but we in the statement we are asking about the electrons in the orbital, and we say that orbital just can contain just 2 electrons. So be careful about that, what you are asking. You can put the correct answer in the option. So we will not consider this because the questions is about the orbital, not about the subshell. So the answer will be equal to 2. And we know that each orbital can contain just 2 electrons in it. Next are the electronic distributions. Electronic distributions are basically the placement of electrons in the each orbital, and each orbital means s, px, py, pz, and dxy. Similarly, there are many orbitals for the different subshells. So basically the arrangement of electrons in the different orbitals is called as electronic distributions, and this is represented by the different rules. And now we know that these rules are Aufbau principles. The second one is Pauli exclusion principle, and the third one is called as Hund's rules. And before using these rules, we have to use the n plus L rule for the correct arrangement of subshell. This correct arrangement is mean that we have to consider the first shell first, then second, then third. So here are the some subshell that are represented by the 1s, 2s, 2p, 3s, and 3d. While this n is basically representing that this is the one shell, and this 2 is called as principal quantum number. That is also tell us about the shell number, and this 2 will be n equal to 2, and 2 also will be equal to 2, and this n represented as we have 3 third subshell and the s subshell of third shell. And similarly, this is showing that d subshell of third shell. So this S1 is represented by the L for S is equal to 0, and for P equal to 1, and similarly for D, L value is equal to 2. So to arrange the electron or shell, we have just used the N plus L rule to arrange the number of subshell in the correct sequence, so that we can follow this rule to put the different number of electron in them. So the first rule is Aufbau principle, that is about the that is according to the electrons energy. So what this rules say that the electrons should be filled in energy subshell in order of increasing energy value. This means that the 1s that is closer to the nucleus have lower energy. The 2s that is far away from the nucleus will have more energy than the 1s, and similarly this 2 represented that this 2s and this 2p both are in the same shell, so the 2p will have higher energy than the 2s shell, and similarly then the 3s and 3d will also have higher energy than the 2p and 2s. This means as the number of shell or as the number of principal quantum number increase, the energy of the subshell increase continuously. So the principle also state that, and we can say that we have to put electron in order of increasing energy, and similarly first we will put electron in the first, then with the 2, then with 2p, and so on we will goes on. And there here is a questions about the Aufbau principle. Which one of the following is following violates Aufbau principle and deviating the Aufbau principle? So here are the options: 1s2, 2s2, 2px2, and we know that both and the just one orbital can contain just 2 electrons. So this is the electronic configuration of carbon, I think so. So this is the electronic configuration of carbon, and we have to put each electron by their increasing order of their energy. So the energy of all 2p are greater than the 2s, and 2s energy is greater than the 1s. So which one of the following is not according to the Aufbau principle? So that will be the option of this, because here we can see that this subshell has 2 electron according to energy, and this 2s have same electron according to their energy, and this 2px have 2 electron, this 2py have 2 electrons, while this 2pz that is higher energy, that is in higher energy than the 2py, do not have any electrons. So that is showing the or disagreement with the Aufbau principle, mean that this option is according to the Aufbau principle and this option is against the Aufbau principle, because we have to place each electron in each subshell by their increasing energy. Next rule is called as Pauli exclusion principle. Pauli exclusion, and you can remember this rule by just exclusion word. So it means that it is impossible for 2 electrons to reside in the same orbitals. This means never 2 electrons can reside in the same orbital of the Pauli electron atom that have same quantum number value for the 4 quantum numbers, and we can represent this by this means that if this is the px orbital and this is py and this is pz, so that contain one electron in this direction, and that is opposite direction, and that is in this direction, and that is in this direction. So the Pauli exclusion principle state that you cannot put the two electrons in the same orbital with the same orientations. This means that never two electrons can be placed in the single orbitals with the same orientation or similar spin. This means that both have +1 or anti-clockwise orientation, and that is not correct for the magnetic quantum number. So this rule is according to this rule stating that you have to exclude electron from the each orbital that have same orientation, and you have to put in the next subshell or next orbital to represent the electron in the orbitals. So it is impossible for two electrons to reside in the same orbital with the same orientation, and that is Hund's rule, and that you can remember by the hand rule. And this explained that you all your hands have 5 fingers. This means we have different degenerate orbitals, and these degenerate orbitals are by the different magnetic quantum number. So each finger will contain 2 electrons. So if degenerate orbitals are available and more than one electrons are placed in them, they should be placed in the separate orbitals with the same spin rather than putting them in the same orbital with the opposite spin. And these can be explained as by. So we can consider the example of carbon. Carbon contains 6 electrons, and the first shell contains just 2 electrons. The second shell contains 2 electrons in the 2s and 2p that contain 4 electrons. So these p orbital have basically 3 orientation that are represented in the px, that is 2px, that will be 2p y, and the last one to be 2p z. So we can place these electron here as singly by in each, and that the electron that's left will be placed with the last or with the px by the opposite spin. So similarly, and this rule is stating that if degenerate orbitals are available, means if these orbitals are, we cannot put these electron in this way. You cannot put this electron, oh sorry, this electron here with the opposite spin. And this stating that if the degenerate, that is a degenerate orbitals, all of these are degenerate orbitals, and if degenerate orbitals are available, you have to put this electron in the left one degenerate orbital for the rather than the opposite spin. So that is a Hund's rule by the electronic distributions. These are 3 rules that we can follow to fill the different number of electrons in the each subshell. So now we will discuss the energy levels of electrons, and that is by the electrostatic attractions of the atoms. So according to the Bohr model, electrons revolve in the circular path of the around the nucleus, and you know that nucleus is a positive and electron is negative. So there are electrostatic attraction between the nucleus and electron, that is called as electrostatic attractions. And the energy between both of these can be calculated by plus kinetic energy with including as potential energy, because electron is revolving around the nucleus at some distance. Because this electron is revolving at some distance, so there is a attraction force between both of them, and that will be represented by the potential energy. And also the electron is revolving around the nucleus, that will represent its kinetic energy. So the total energy of the electron can be represented by the sum of potential energy and sum of kinetic energy. Now we can put this formula here, that Z is the number of charge present on the nucleus, and E square is the charge of both nucleus and the electrons. This E basically is the multiplication of 2E, and here is the constant 4 pi epsilon naught into distance. And this is the formula of kinetic energy, 1 by 2 into mv square. So the so the conclusion of both of these formula can be written in the form of that, and this all with the minus sign is the constant, or can be calculated by the different constant for hydrogen atom. So this representing that 1 over n square mean the different subshell of the electrons will have different energy. And it also represented that if the number of shell for electron increases, the number of energy of electrons will be increased, because this is the minus sign here. So to count the number of count the energy of electron, you have to use this formula for the calculation of energy. So this is the formula to calculate energy of the electron in any shell. For first shell, you have to put n equal to 1 and take the square of 1, and that answer will be equal to 13.13 kilojoule per mole of the electron energy. And for the second shell, you have to put n equal to 2 and take the square of 2, that will be equal to 4, and divide 13.13 divided by 4, and the answer will be something. Similarly, you have to put different number of shell to count the energy of different shell, and the answer will be in the decreasing form. But this minus sign showing that the answer is going close to 0. So this means that this energy is not decreasing, while the answer is increasing in the going close to 0. And at some extent, the answer will be equal to 0. And we can say that electron is at the infinity state. And also you can count the radius of electron by formula R equal to n square into 0.529 angstrom. And this n square is represented the principal quantum number, and you can put n equal to 1, n equal to 2, n equal to 3, whatever you can put in them, or you have to count every or at any shell energy. You have to put just number in the replacement of n, and just have take square of that and multiply with the 0.529. So next, here are the questions. Orbitals having same energy are called as hybrid orbitals, degenerate orbitals, valence orbitals, or the d orbitals. Orbitals that having same energy are called as degenerate orbitals. because the magnetic quantum number that are discussed here, these orbitals are basically used in the chemical bonding of different compound or chemicals. So there are different orientations we have to use for them. And for S we can use circle, and for P we can use dumbbell shape, or for D shape we can use double dumbbell, and for the F we can use complicated shapes. So these shapes will be used in the next chapter of chemical combination or chemical bonding for different formations of the compound. So now in the absence of magnetic field, all the degenerate orbitals have same energy. That's why these are called as degenerate orbitals. So orbitals having same energy are called as degenerate orbitals, while the hybrid orbitals also have same energy, same shape, and same size. So they are not called as orbitals, but they are different in terms from the degenerate orbitals. When 6d orbital is complete, the entering electron goes to, and this is according to this will be according to the Aufbau principle. So we know that the coming electron will be goes to the some first with the decreasing energy, and then to the highest energy. So if 6d is complete, then come with the 7. So you have to just first count the n plus l rule for this. We can use artboard here. So okay, we have 6d. This means this is n and this is l. So n equal to 6 plus 1, and the d represent SPD, and this is 2. This means the total answer will be equal to 8. And in the statement we know that if 6d orbital is filled, then the electron will come in the next shell that will be equal to 7, and that can be S, that can be P, but you have to choose the right answer, because we have to follow the Aufbau principle, and we have to use the energy sequence of the electrons that will be in the, these are the option 7f. 7f means 7 plus 3, that will be equal to 10. 7 plus s, 7 plus 0 equal to 7, and this 7p means 7 plus 1, that will be equal to 8. This means that will be same with the 6d, because the answer for 6d equal to 8, and for 7p the answer will be equal to same 8. So for 7d the answer is 7 plus 2, that will be equal to 9. So we know that electron first come with at the lowest energy level, that will be represented in the 7s, that is lower than the 6d or 7p. So electron will come in the 7s subshell. So here are the formula you can use to calculate the energy difference between the subshells or shells. So in the first shell, we'll consider the diagram of electrons or atoms that are revolving around the nucleus. So you can count the difference of energy between N1 and N2. Similarly, you can count the number of energy between N3 and N2, and so on. You can calculate whatever you want. So here is a simple formula to count the energy difference between the different shell. So this all terms can be calculated, and the answer will be equal to 2.8 into 10 raised to power minus 18 joule. And for calculating the energy difference, you have to put the number of shell here, and one will be the higher number of electron, and you can say that from the shell that is electron is jumping will be put here, and the shell that where the electron is coming, you have to put the number here. So we can just take an example by considering that if electron is jumping, here is a nucleus, and that is a first shell, that is second, and that is third, and we can say that that is N1, that is N2, that is N3. And we can assume that if electron is jumping from N3 to N1, so it means that we have to put 1 by 3 square minus 1 by 1 square. So you can calculate this term, and after calculating, you have to multiply this by the 2.18 into 10 raised to power minus 18 joule. So the answer will be the difference of energy between these two shells, that is here. So the energy difference between this will be equal to the answer that you have calculated after this calculation, and this will be something in the joule, can be X or whatever, that will be the answer. So these are the electronic transition. Electronic transitions are basically the number of spectral lines or number of different lines or light that is emitted by the jumping electrons from any shell to another shell. So different spectrum or different number of photons that are emitted by the electron during the transition are called as electronic transition. And you can use the formula for calculating the different number of transition. Considering we have question, calculate the energy of electron in the fourth shell, and next is the question like that. So if we assume that electron is jumping, this is the electron nucleus, this is the first shell, that is N1, that is N2, and that is N3, and that is N4, and so on, whatever it will be. If we count, if you are asked about the questions, how many number of lines will be originated by jumping electrons from N shell 4th to N shell 3, count the number of spectral lines. So we know that N2 is equal to, that is our N2, that is equal to 4, and from where the electron is coming, and that is N1, where the electron is coming, and that is 3, or sorry, that is 2. So we have to use a simple formula that number of spectral lines equal to n, that is equal to 4. Put the formula 4 equal to -2 and divided by this by 2. So the number of lines will be 4 minus 2. The answer will be 2 into 4, and answer will be 8 divided by 2. So there are 4 number of lines that will be originate, or transition lines will be 4 by jumping electron from n4 to n2. Or similarly, you can count the number of lines by number if electron is jumping from 5th to n1. So you have to just put the value of n here, 5 minus 1, that will be equal to 4 into 5, that is will be equal to 20, and 20 divided by 2, that will be answer 10. So 10 lines will be originated by the jumping of electron from shell 5 to n1. And similarly, you can count the number of lines by opposite jumping. If electron is jumping from n1 to n5 shell, or electron is jumping from the n2 to n3 or n5 shell. See, just you have to put the number of shell here and just calculate, and the answer will be like that, how many number of lines will be there for the jumping electrons. So now the last question is that calculate the energy of electron in 4th shell. Okay. Energy equal to 1313.13 divided by n square, and we know that we are asked about the n shell is 4th, so we can put 4th here, and that will be 13, and that will be equal to that same answer, and division in the 16. So you have to divide it 13 by the 16 to count the energy in the 4th shell. So that will be the answer of energy in the 4th shell. So that is our topic for the electronic transition for today. If you have any question regarding the energy levels, energy transition, and orbitals or quantum numbers, you can ask freely.
Guys, it's clear because the class going to be finished right now.
Yes, teacher.
Okay, guys, you have to be dependent for the time
Yes.
because here in the United States we have the time changing here in the United States. Now in the United States it's 11:27. I know maybe in South America like Colombia, Ecuador, we have 1 more hour than you. In your country, I think, for example, in Ecuador, I think it's like 10:27, okay? And the classes start 10 a.m., okay? When here is 10 a.m., in your country maybe it's 9 a.m. You have to depending, okay, because the time is changing, okay? So, okay, guys, thank you so much. Thank you, Elias. Have a wonderful day for you.
Mm.
And thank you, guys.
Thank you.